Okay, so for our project, with the known parameters using ANSYS Fluent, we look to export that data to Solidworks in order to derive the CFD and FEA interactions between the fluid flow and the surrounding body to determine the stresses imposed on the rocket during our flight. Okay, first we're going to go over the derived geometry, which is following that of our actual rocket, and then I'll go over the meshing and meshing quality to the boundary layers and conditions and the models used, and then the actual ANSYS results, and then the procedure we use to export those ANSYS results to Solidworks, and then our actual Solidworks derived inputs and results. Okay, and so first you go and create your Solidworks model, and you go and import it. It's already been done here, and so you import it and go into the design modeler. And once you click generate, you should see your import geometry. And from here, we created an enclosure around it. As you can see, I refined it just a little bit, so there's a little bit more of a tail end. And from here, we go and subtract out the Boolean. Pause it real quick.
Let's go.
Okay. Okay, so from here, we chose to do our meshing with Fluent meshing, and so what you would normally do is go and you would drag this over to here, and then you connect your geometry to the mesh. And once you do that, you can open up the Fluent model. And from here, there's going to be a tab to import your geometry. You go and just create it, and that'll create your geometry in the section shown here. And so for us, we chose to add just a small local sizing just around the perimeter of the body of about 3.8 millimeters. And then you create a surface mesh, and then for us, you can kind of see what we used here. The only thing is that with these sizing is that they have to align with the minimum and maximum values chose for this and the generated volume mesh. And so from there you go and you describe your geometry. So for us, we're using a fluid region with no actual voids. And you just update your boundary layers, and if you do your name selection correctly, it should do this automatically for you. And you update your fluid regions, and then for us, we also chose to create a boundary layer. I'll show here a little bit around the rocket with 10 layers, and then from here you can just create your volume mesh with our minimum cell size of about 7 millimeters. And so if we zoom in here, you can kind of see the total volume of the mesh. But if we zoom in, we can kind of see as the boundary layer around the rocket. So you can kind of actually count 1, 2, 3, 4, 5 up to 10 for the boundary layer.
So basically what we did here was created a Boolean to subtract the geometry of the rocket out of the cube that surrounds it. Alright, so this is our SolidWorks model of the rocket with the pressure curve forces applied along the body of it. You can see the pressure increases along the length of the nose cone and along the length of the body. We're still playing with the equations, so that's subject to change, but we're fairly confident in the results for the fins. So here's a snapshot of the fin von Mises stress, and we found that the highest stress point is on the inside notch. Here's a section view of it. You can see right here on this inside edge. It's actually below a safety factor of 1, but SolidWorks doesn't take into account the amount of epoxy that is on it. An area of concern from another FEA run was the top centering ring. here's a sectional view of the centering ring from this FEA run due to the pressure on the rocket. So a quick note about the safety factors. The pressure FEA run yielded safety factors that were less than 1 for the fins. It's kind of hard to judge on if that actually mattered or not. It's difficult to model because the rocket did have a successful launch and did not break.
Okay, and so from here you open your Fluent model, and so for us we opted for a density based as our density isn't constant, and then we turned on the energy equation as it's important for the fluid flow, and then we opted for the K omega SST model as we're more concerned with the boundary conditions near the rocket wall. And then our fluid is just obviously air, and we set our density to ideal gas as, again, it's not constant. And then for our boundary conditions, we set our velocity inlet to our actual in-flight velocity. That was found to be 118 meters per second. And then the outlet was just set as a normal pressure outlet with a gauge pressure equal to 0, as you can see. And then for our residuals, we had them set to 185. And then we initialized just based on the inlet location. And then after running our calculations, we can see here our resulting values. These are the important ones. Right here, our shear stress and our pressure contours, as these are the actual data that we'll be using to export to Solidworks. And so from ANSYS, there's an option down here for your XY plot. If you open that, you can export it to, if you write the file, it will write a CSV file to your desktop, and from there you export your CSV file to an Excel file, which is what we have here. And so you get your shear stress and pressure contours, and then based on that we created a equation based on each section, our nose cone, our airframe, and across the fins. And from there we export these equations to Solidworks, where they can then derive the stress and strain on the rocket.
Okay, so once those equations are produced, come over here to Solidworks to examine the stresses due to the pressure. This is how we did it. Use a non-uniform pressure distribution. You have to create a reference geometry or coordinate system. Come down here, and here's the equation. Now we had a lot of headaches inputting these equations in here because Solidworks wants it in here a specific way. As you can see, the X has quotations around it. Took us a little while to figure that out, but we got it working, and this is what it looks like for now. We're gonna still mess with it and refine it as much as we can to get most accurate results.